Hey stats folks, so we're going to pick up where we left off yesterday. So recall that we have a population where we don't know the population mean. We take a sample, we get a sample mean, and we use that to create a confidence interval, okay, that places that population mean within that. All right, and we're going to just start up with a warm-up today, just kind of a basic problem like we did yesterday, and then we're going to put a little twist on it with our second problem of the day. So here we go. A random sample of 40 farming regions have given a sample mean of $6.88 per 100 pounds of watermelon. Assume that the population standard deviation is $1.92 per 100 pounds. Find a 90% confidence interval for the population mean price. All right, so we have a sample of size 40. Okay. Now, notice, we didn't say anything about the distribution of the population, but we do have n is greater than or equal to 30. So we've met that criteria. We also know the population standard deviation, okay, is $1.92. Okay. So when we go back to our criteria here, okay, we have a random sample, population standard deviation is known, and we have a sample size of at least 30. So we've met our criteria. All right, what else do we have? Now, that sample had a mean of $6.88. And remember that X bar is a point estimate for mu. Our estimate for the population mean is $6.88. Okay? But what is our confidence interval? So we want a 90% confidence interval. So recall that we have z-scores for each of our confidence intervals that were created so that the area within those z-scores is what we want. And the z-score for a 90% confidence interval is 1.645. Okay. So now that we have that, we're ready to calculate our error. This is our estimate. But knowing the standard deviation of the population and the sample size, what's the error? How far off could we be with our estimate of mu? So, error formula. Remember, it's the critical value, the z-score for our confidence interval, times the population standard deviation divided by the square root of n. Remember, that's the standard deviation of the X bar distribution. So our error here is going to be 1.645 times 1.92 over the square root of 40. And this gives us an error of about 0.4993. So I'm going to round that to 0.5. Okay, 0.50. So our estimate for mu is 6.88. Our error is 0.50 cents. So what do? We take that estimate and we add the 50 cents and subtract the 50 cents to create our interval. So I'm going to take 6.88 minus 50 cents. I'm going to put mu between it, and 6.88 plus the 50 cents. So I get 638 to, what is that, 738. We end up with a width of $1, right? So let's finish with the statement. And this is important. I don't want just this answer. I want you to actually say what you know here. We are 90% confident that the actual mean price per 100 pounds of watermelon is between $6.38 and $7.38. Okay, and that's what we get to say. Now, there's a 10% chance that we're wrong, but we're 90% sure that mean is between 638 and 738. Excellent. So in this, what are we doing? We're taking a sample, and then we're calculating our error. Okay? Now, consider this. Would there be times where you want to set a particular error? In this one, we had no idea how big the error was. It ended up being 50 cents. But would it be possible that we could have an error like of $1.50 or $3 or something like that, and that error is so big that really our result isn't very meaningful? Like if my statement here were to say, we're 90% confident that the actual mean price per 100 pounds of watermelon is between $2.38 and $10.38. Well, that doesn't really help us at all. That's such a huge range, right? So would it make sense for us at times to say, you know what? We want our error to be this. We want our estimate to be within a certain amount. Okay? So then if we set that error, what could we do with that then? Okay? Well, we can't change what the population standard deviation is, but maybe we could change what our sample size is. Can we set an error and then find a sample size that will meet that error that we want? And think about this. The larger the sample, what with our interval? The narrower, right? The bigger the sample that we have, the smaller our interval is going to be, right? Because we are dividing by n down here, right? And when we divide, if this number gets bigger, when we divide, we get a smaller number. We get a smaller error, and that should make sense. The more of the population that we have, the more confident, Mark, I got to be careful with that. The narrower our confidence interval level should be. So let's look at a problem like that. A wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. The standard deviation for the weight of the salmon is 2.15 pounds. How large of a sample is needed to be 99% confident that the sample mean is within 0.2 pounds of the true mean weight? Okay? So when we see that within 0.2 pounds, that's our error. Okay? So we have E equals 0.2. All right? Okay. Now, what else do we have here? The standard deviation for the weight of the salmon of the population is 2.15. We want a 99% confidence interval to have that error of 0.2. So our critical value, our z-score for 99% confidence interval is, what is that number again? It's 2.575. Can we find n? All right, well, how's our error formula go? Okay, let's substitute in. 0.2 is the error. Our z-score 2.575. Our standard deviation is 2.15 over, we want to find the square root of that. All right, so let's solve that. Okay, let's divide by 2.575. That's a really unpleasant decimal there. So I'm going to write that net number is about 0.078, but I'm actually going to use my calculator number, not that rounded number. That equals 2.515 over the square root of n. Now, how do we solve this? Remember, that n's down in the denominator, and if I rewrite this as a proportion, I can use a cross product. Okay, so 0.078 times the square root of n equals 2.15 times 1. And I'm going to divide by this 0.078. That's going to cancel these out, and then I can square it to get to the n. So I'm going to type in on my calculator 2.15 divided by, I'm going to grab this 0.078 number from my calculator, so I'm not using that rounded number. I'm going to close the parentheses and then I'm going to square it. And I get n of 766.25. So this is the sample size that will create an error of 0.2. Now, can we have a sample of 666.25 salmon? No. So do we round it down to 766? We wouldn't do that either, because that makes our sample size a little too small to have our error. Okay, when we're talking sample size, we always want to round up. The bigger the sample, the smaller the error is. If I round this down, it's going to cause my error to be a little bit smaller. So our sample is going to be 767 salmon. Now, I want you to notice this too. Remember to use this error formula that our population has to be normally distributed. And we weren't told that up here. Okay? And if it's not normally distributed, we have to have a sample size of at least 30. And did our sample size be at least 30? Yes, so we can be confident that our error is really 0.2. Now, if this sample size ended up being 12, we'd say, that's not really going to work unless we knew the population was normally distributed. All right, so more of what we practiced from our last video today. Now we're also throwing in this twist of finding a minimum sample size. Now, could we have a sample of 800 salmon? Yeah, that would have an error smaller than 0.2, right? This is the minimum sample size, so we can find that. One other comment I'm going to make, in your practice, there'll be some where you actually have the data. So you're going to have to find X bar yourself. All right, thanks for watching. We'll see you next time.